There's a brutal truth about space exploration that nobody wants to hear. It's not just difficult or expensive or dangerous. It might be fundamentally impossible at scale because of the harsh realities of energy, physics, and the economic systems that govern human civilization. Michio Kaku has spent decades promoting the wonders of space and the potential for humanity to become a spacefaring civilization. But he's also honest about the constraints we face, constraints so severe that they might make space exploration a dead end rather than humanity's future. The problem isn't imagination or ambition. The problem is energy. Specifically, the relationship between energy costs, rocket physics, and the fossil fuel economy that makes launching anything into space barely feasible. When you examine the physics honestly and calculate the energy requirements realistically, space starts looking less like humanity's destiny and more like an expensive hobby we can barely afford. The core issue is the rocket equation, a mathematical relationship discovered in the 19th century that governs all rocket-powered space travel. The equation is unforgiving. It says that the final velocity of a rocket depends on the exhaust velocity of the propellant and the natural logarithm of the initial mass divided by the final mass. In simpler terms, to go faster or carry more payload, you need exponentially more fuel. And that fuel has mass, which requires more fuel to lift, which has mass, which requires even more fuel, in a vicious cycle that makes space travel inherently inefficient. Kaku explains this with a sobering example. To launch 1 kilogram of payload into low Earth orbit, about 250 miles up, requires roughly 50 to 100 kilograms of rocket and fuel. That's a 50 to 1 or 100 to 1 mass ratio. Most of what you launch is fuel to lift fuel, with only a tiny fraction being useful payload. And that's just to reach orbit, not to go anywhere beyond Earth. To send that same kilogram to the Moon requires several times more energy. To Mars, exponentially more. To the outer planets, the energy requirements become absurd. This wouldn't necessarily be a problem if energy were cheap and abundant, but it's not. Energy, particularly the kind needed for rockets, comes primarily from fossil fuels. Rocket fuel is typically refined petroleum products or liquid hydrogen and oxygen, both of which require enormous energy inputs to produce. Even when we extract hydrogen from water through electrolysis, we're using electricity that mostly comes from burning fossil fuels. The amount of energy required to launch payloads into space is staggering. A single space shuttle launch consumed about 3.5 million pounds of propellant. That's roughly equivalent to the energy in 750,000 gallons of gasoline, or the energy consumption of 2,500 American homes for an entire year. And the shuttle only carried about 50,000 pounds of payload to orbit. The energy efficiency is terrible, and physics says it can't be dramatically improved with chemical rockets. Now multiply that by what would be needed for serious space exploration and colonization, building a moon base, establishing a Mars colony, mining asteroids, creating orbital habitats. All these ambitious visions require launching millions of tons of material and equipment into space. The energy requirements would be a significant fraction of global energy production. We're talking about consuming the equivalent of multiple years of global fossil fuel output just to establish basic infrastructure beyond Earth. Here's where the oil dependency becomes critical. The entire aerospace industry, indeed the entire industrial civilization, runs on fossil fuels. Rockets are powered by fossil fuels or by hydrogen and oxygen produced using fossil fuel energy. The factories that build spacecraft run on fossil fuels. The transportation networks that move components run on fossil fuels. The power grids that support everything run primarily on fossil fuels. Space exploration is completely dependent on cheap, abundant fossil fuel energy. But fossil fuels are finite. Oil production will eventually peak and decline. Natural gas will follow. Coal might last longer but comes with severe environmental costs. And critically, we need to transition away from fossil fuels to avoid catastrophic climate change. The same energy sources that make space exploration barely possible are cooking the planet. We're facing a fundamental conflict between maintaining industrial civilization, transitioning to sustainable energy, and pursuing expensive space ambitions. Kaku points out that renewable energy sources like solar and wind while essential for sustainability, are not dense enough or easily transportable enough to support the massive concentrated energy demands of rocket launches. You can't run a rocket on wind power. You could theoretically produce rocket fuel using renewable electricity, but the efficiency losses in conversion make it economically prohibitive at scale. Solar-powered electrolysis to create hydrogen fuel is technically possible, but requires enormous solar farms and energy inputs. The economics become impossible to justify. If we're transitioning to renewable energy, every unit of energy becomes more precious. Using renewable energy to produce rocket fuel means not using that energy for essential needs like electricity, heating, transportation, industrial production. Why would a future sustainable civilization divert scarce renewable energy to launch rockets when that energy could power homes, hospitals, and farms? The physics of energy return on investment also works against space exploration. On Earth, energy invested in extraction returns more energy. Drilling for oil returns 20 or 30 times the energy invested. Even renewable energy, once infrastructure is built, returns multiples of the energy invested in construction. But space exploration has negative energy return. Every joule spent launching a rocket is gone, consumed, never recovered. You might bring back knowledge or samples, but no energy. You might mine asteroids for materials, but the energy cost of retrieval far exceeds any value gained. The only way space exploration makes energy sense is if you find vast new energy sources in space. Which brings us to the supposed solution: space-based solar power, mining helium-3 from the moon for fusion, or harvesting resources from asteroids. But each of these ideas faces chicken and egg problems. You need cheap space access to develop space resources, but you need space resources to make space access cheap, and you need enormous upfront energy investment with no guarantee of return. Space-based solar power, for instance, requires launching thousands of tons of solar panels, framework, transmission equipment, and receivers into orbit. The energy cost of launching all that material would take decades to recoup, even if the system worked perfectly. And it's never been built at scale, so we don't know if it works at all. The concept is theoretically sound, but practically dubious and economically insane given current launch costs. Helium-3 fusion faces even worse obstacles. Fusion doesn't work yet, despite decades of research and billions in investment. We might never achieve net positive fusion energy. Even if we do, helium-3 is rare on Earth but supposedly abundant on the Moon. But mining the Moon, transporting helium-3 back to Earth, and using it in fusion reactors that don't exist yet, all requires more energy than we're likely to gain. It's a fantasy solution to a real problem. Asteroid mining gets promoted as a solution to resource scarcity, but the energy economics are brutal. Yes, asteroids contain metals, water, and minerals, but reaching them, processing materials in space, and returning them to Earth or using them in space requires enormous energy investment. Why spend the energy equivalent of years of global production to mine asteroids when we can mine Earth with far less energy cost? The only materials worth retrieving from space are those physically impossible to get on Earth, and there aren't many of those. Kaku emphasizes that the laws of thermodynamics are unforgiving. Energy can't be created or destroyed, only converted from one form to another, always with losses. The efficiency of chemical rockets is about 3%. That means 97% of the energy in rocket fuel is lost to heat, exhaust, and other inefficiencies. Even the best theoretical chemical rockets can't exceed about 5 to 10% efficiency. The physics fundamentally limits how efficient rockets can be. Alternative propulsion systems all face their own energy problems. Nuclear rockets would be more efficient, but require vast infrastructure to build, test, and launch safely, plus political will to accept the risks of launching nuclear materials. Ion drives are efficient, but low thrust, requiring years to accelerate and requiring nuclear or solar power sources. Solar sails need no fuel, but provide minuscule acceleration and only work in the inner solar system where sunlight is intense. Each proposed solution requires more energy upfront than it saves. It's like trying to bootstrap your way to wealth by borrowing money at high interest. You can do it if returns exceed interest, but if returns are negative or marginal, you go bankrupt. Space exploration, judged purely on energy returns, is bankruptcy. We're spending energy we generated from finite fossil fuels to launch things into space with no energy return, making us collectively poorer in energy terms. The scale problem makes this worse. Putting a few astronauts on the Moon or even Mars might be possible if we dedicate enough resources, though as Kaku has noted, even that faces immense obstacles. But creating self-sustaining space civilizations requires moving millions of tons into space. Building O'Neill cylinders, large rotating habitats that could house thousands of people, requires launching structural materials, shielding, atmosphere, water, equipment, and supplies totaling millions of tons. At current launch costs of roughly $2,000 to $10,000 per kilogram to orbit, launching 1 million tons would cost between $2 trillion and $10 trillion. That's just the launch cost, not the cost of building the habitat or systems. And that's for one habitat. Multiple habitats, moon bases, Mars colonies, the costs compound into fantasy territory. No economy can sustain that level of expenditure for infrastructure that produces no economic return. Even if launch costs drop dramatically, say to $100 per kilogram through reusable rockets and mass production, launching 1 million tons still costs $100 billion. That's more than most nations' annual space budgets by orders of magnitude. And physics says launch costs can only drop so far before hitting fundamental limits imposed by energy requirements and the rocket equation. The dream of space elevators or orbital rings that could reduce launch costs by circumventing the rocket equation face their own physics problems. A space elevator requires materials with strength-to-weight ratios that don't exist yet. Carbon nanotubes theoretically could work, but manufacturing kilometers-long nanotubes without defects is currently impossible and might remain so. Even if developed, building a space elevator requires massive energy investment, with uncertain returns and decades of construction. Kaku also addresses the time problem. Space distances are so vast that even traveling at high speeds takes years or decades. Chemical rockets can't achieve velocities much above 40,000 miles per hour relative to Earth without using gravity assists. At that speed, reaching the nearest star system, Alpha Centauri, would take over 70,000 years. Even reaching the outer planets takes years. Time is energy in a different form. The longer a journey, the more life support, more shielding, more equipment needed, all requiring more energy to launch. The supposed solution, traveling at high fractions of light speed, requires energy inputs that dwarf anything achievable. To accelerate even a small spacecraft to 10% of light speed requires energy equivalent to multiple years of global energy production. To accelerate a crewed starship with life support and supplies to that speed requires energy inputs approaching the total energy output of the Sun. The physics makes interstellar travel with conventional energy sources effectively impossible. Some propose antimatter propulsion, which could theoretically provide the energy density needed for relativistic travel. But producing antimatter requires particle accelerators consuming vast amounts of energy to create minuscule amounts of antimatter. Current production rates are measured in nanograms per year. To fuel a starship would require millions of tons of antimatter, which would take millions of years to produce at current rates, using more energy than human civilization has ever generated. The fundamental problem, Kaku argues, is that we're a Type 0.7 civilization on the Kardashev scale, not yet able to harness all the energy of our planet, trying to do things that require Type 1 or Type 2 civilization energy resources. We're children playing with expensive toys, not a mature civilization with the energy abundance needed for serious space expansion. Even defending Earth from asteroid impacts, often cited as a reason for space infrastructure, faces energy problems. Detecting threats requires space telescopes and monitoring systems. Deflecting asteroids requires missions capable of intercepting objects traveling at tens of thousands of miles per hour, matching trajectories, and applying force to alter orbits. This requires enormous energy, and it needs to be maintained constantly because new threats appear regularly. The energy cost of comprehensive planetary defense might exceed what we can afford while maintaining civilization. The oxygen problem in space also relates to energy. Humans need oxygen constantly. In space, oxygen must be produced through electrolysis of water or recycled from carbon dioxide. Both processes require energy. A crew of 4 astronauts needs roughly 3 kilograms of oxygen per day. That doesn't sound like much, but producing it through electrolysis requires electricity, and storing it requires pressurized tanks, which have mass that must be launched. Over months or years, the energy costs compound. Water recycling faces similar issues. Every system requires energy to operate. Filters need power. Purification needs power. Temperature control needs power. And in space, all that power must be generated by solar panels, nuclear reactors or batteries, all of which add mass to the spacecraft, requiring more fuel to launch. It's cumulative inefficiency, stacking inefficiency on inefficiency. The psychological and biological costs of space travel also translate to energy costs. Keeping humans healthy in space requires exercise equipment, medical supplies, varied food, psychological support systems, communication with Earth, entertainment, all requiring mass and power. Robots don't need any of this. They don't require oxygen, food, water, temperature control, or psychological care. They can enter hibernation when solar power is insufficient. From an energy efficiency standpoint, sending robots instead of humans makes vastly more sense. Kaku suggests that we might be fundamentally misunderstanding our role in the universe. Perhaps biological intelligence is a transitional phase, not the end state. Perhaps silicon-based intelligence, artificial intelligence, is the form that spreads through the cosmos because it doesn't require expensive life support, doesn't suffer from radiation damage the same way, doesn't need food or water or oxygen, and can survive journeys lasting centuries or millennia without aging or going insane from isolation. If that's true, then human space exploration might indeed be a dead end. We might explore the solar system robotically, sending AI-driven probes that can operate for decades or centuries on minimal energy. But humans might never leave Earth in significant numbers because the energy costs are too high and the benefits too low. We'd remain a planetary species while our mechanical descendants explore the cosmos. The climate crisis makes this trajectory more likely as we struggle to transition away from fossil fuels and build sustainable energy infrastructure. Dedicating vast resources to space exploration becomes harder to justify. Every dollar and every joule spent on space is a dollar and joule not spent on climate mitigation, renewable energy development, sustainable agriculture, or adapting to environmental changes. The political reality reinforces this. Space programs require sustained funding over decades, but climate impacts are happening now. Rising seas, extreme weather, crop failures, mass migrations. These are immediate crises demanding immediate resources. Future space colonies can't compete for funding against present disasters. The money that might have gone to Mars bases will go to seawalls, drought relief, and renewable energy instead. Kaku doesn't necessarily advocate for abandoning space exploration entirely, but he argues for clear-eyed realism about what's possible given energy constraints. Small-scale exploration, robotic missions, scientific satellites, these provide value and remain affordable. But dreams of massive space colonies, terraforming planets, or becoming a spacefaring civilization require energy abundance we don't have and might never achieve. The oil age made space travel possible, but only barely. As oil becomes scarcer and more expensive, as we transition to renewable energy with lower energy density, space travel becomes even more prohibitive. We might look back at the 20th and 21st centuries as a unique window when fossil fuel abundance made space exploration temporarily feasible, a window now closing. The laws of physics don't change based on human desires. The rocket equation remains unforgiving. Thermodynamics can't be negotiated with. Energy density of chemical bonds limits what chemical rockets can achieve. The speed of light caps how fast anything can travel. These aren't engineering challenges to be solved with cleverness and effort. They're fundamental constraints built into the structure of reality. Perhaps the solution, if there is one, involves radically different approaches. Generation ships that take thousands of years to reach other stars, with successive generations born and dying in transit. Microscopic probes accelerated by ground-based lasers to relativistic speeds, arriving as data rather than physical presence. Digital consciousness uploaded and transmitted as information, reconstituted in robotic bodies at the destination. Mind-bending ideas that sidestep rather than solve the energy problems. Or perhaps there is no solution. Perhaps the universe is structured such that biological intelligence remains planet-bound, able to study the cosmos through telescopes and probes, but never to physically travel its vastness. Perhaps every technological civilization throughout the universe reaches the same energy wall, the same realization that space, while fascinating, is simply too expensive to colonize. The silence of the cosmos, the Fermi paradox, might be explained by this energy barrier. Advanced civilizations exist but stay home because leaving is economically and energetically irrational. They focus on sustainable life on their home planets rather than wasting resources on space expansion. They explore virtually rather than physically, building simulations more interesting than reality at a fraction of the energy cost. Kaku's ultimate message is one of constrained optimism. Space isn't entirely a dead end. We can and should explore robotically, maintain satellites for communication and Earth observation, conduct science from space platforms, perhaps even establish small research bases on the Moon or Mars. But massive space colonization, interstellar travel becoming a galactic civilization, these might remain forever beyond reach because the energy costs exceed any possible returns. We are, fundamentally, children of Earth, shaped by its gravity, nourished by its biosphere, protected by its atmosphere and magnetic field. Leaving Earth permanently might be as impossible for humans as leaving water permanently is for fish. We can visit space briefly, at great cost, but we cannot thrive there without bringing Earth with us in the form of massive life support systems requiring vast energy inputs. The dream of space is beautiful, inspiring, central to science fiction and human imagination. But dreams don't alter physics. Energy limitations are real. The oil that made the Industrial Revolution and the space age possible is finite. As it depletes, and as we transition to renewable energy, space becomes increasingly expensive relative to our energy budget. The math is unforgiving. The physics is final. Space might not be humanity's destiny after all. It might be a dead end, an attractive but ultimately impractical direction, limited by the fundamental relationship between energy, physics, and the economic realities of civilization. Understanding this doesn't mean giving up on all space endeavors. It means focusing on what's actually achievable, celebrating robotic exploration, maintaining realistic expectations, and perhaps accepting that humanity's future lies in sustaining and improving life on Earth rather than escaping to the stars. That future might be less romantically adventurous, but it's the one that energy, oil, and physics make possible.